So I'm Jen. I'm an assistant professor at Stony Brook, and as Tehran also said, I'm at the Flatiron Institute. So I'll just, since we started 5 minutes early anyway, I could put in a short plug for this. The Flatiron Institute is a computational center for quantum physics in New York. We're hiring postdocs. It's a postdoc fellowship position, lots of freedom in a really new institute in a nice city. So if anyone is interested in a postdoc position at the Flatiron Institute, then I'll be here for the next couple of days. Feel free to chat with me about it. So this talk is meant to be an introduction to topological insulators. The slides are somewhat adapted from some lectures by Charlie Kane. So these are on the web. And I would also highly recommend, there's many review articles on this subject. The one that I kind of used to prepare this talk is this review article by Charlie Kane and Zahid Hassan. And so I'll have some figures and references from there. So let's get started. What's an insulator? Well, everyone knows what an insulator is. It's something that doesn't conduct electricity. But if we want to think about why does this happen, the reason is that there's no low energy excitation. So if we, for example, plotted a band structure, then we'd see that there's some energy gap. And if we try to apply, if we put a voltage onto this system, and try to excite electrons to move, there's no places for them to be excited to. And so that's kind of an operational definition of what an insulator is. But we already know that not all insulators are the same. And so you've probably seen this in some of your classes. If we put an electron in 2 dimensions in a strong magnetic field, then we also have an insulator by this definition. So an electron in a magnetic field has these flat energy levels, which are Landau levels. And if the Fermi level is lying between these Landau levels, then again, we have no low energy excitations. And so we shouldn't be able to conduct electricity. But we know that this isn't really the case, because if we put a voltage across the sample, then we can get a current perpendicular to this, which is the Hall current. And in particular, the Hall current also has this kind of weird feature where we see these steps in the resistance or in the conductance. And so this is kind of the first example of something that is insulating, but it's not the same as a conventional insulator. And it's not the same in 2 different ways. One is because the current that comes when you apply voltage is perpendicular to the applied voltage. And the other is that we get these quantized steps, which are actually measurable in experiment. So, and so these quantized steps are a hint to us that something different is going on, and that different thing might be related to topology.
There's a pointer if you'd like to use that. I think there's a pointer if you'd like to use that.
Where? Oh, this. Okay. This, I should probably, this has a little one. Is it not visible, actually? This is a bit bigger.
Yeah, this one is.
It's a bit bigger.
If you want to use a USB to use as a clicker as well.
Okay, maybe that would be good. Let's close it. Let's just see what happens. Oh, it seems to work. No, that's fine. Okay, good. So, so the thing about the quantum Hall effect, one, we know it's different than a normal insulator. And the fact that we see these quantized steps is a hint to us that something topological is going on. And so just to kind of start from the beginning, well, what do I mean by topological? What is a topological invariant? A topological invariant is something that doesn't change under smooth deformations. And so the kind of canonical physicist example of this is the donut and the coffee cup. What this picture is meant to show is there's a topological invariant, which is called the genus. And the genus is, if you have some manifold, how many holes does it have in it? And so since the coffee cup and the donut both have one hole, which is the handle or the hole in the donut, then these things have the same genus. And you've probably seen the GIF that turns the coffee cup into the donut. But more relevant to us is the Hall conductivity. It has this same feature, which is we have these steps in the Hall resistance. And these steps are also immune to small deformations of the Hamiltonian. So how do I see this? Well, in this plot, this axis is the magnetic field. We're moving, as we turn up the magnetic field or turn down the magnetic field, we're changing the Hamiltonian, and we're changing it smoothly. And And yet this number remains quantized. And so that's an example of a topological invariant. It's something which takes on integer discrete values, and when you change your system a little bit, that integer value can't change because there's nowhere continuous for it to be able to jump to. So, and so we see that the quantum Hall insulator is an example of a topological invariant. Now, how can we reconcile the current that we see in this state, which has an energy gap in the bulk? Well, the way that we can reconcile this is that these are the Landau levels that we saw in an infinite system. These Landau levels are completely flat, but in a finite size system, the Landau levels will bend up at the edges of the system. And when they do that, you'll see that there actually is a low energy excitation sitting at the edge, even though in the bulk of the system there wasn't. And so the current that we see in a finite size quantum Hall sample is actually coming from these low energy excitations sitting at the edge. And this is a generic feature of a topological state, insulating in the bulk and having low energy excitations at the edges. And that's what's known as the bulk edge correspondence. So there's different ways to see this. So in the picture of quantum Hall states that you might have seen in textbooks, you have these cyclotron orbits, and at the edge of the system, the cyclotron orbit is hitting the edge. This is kind of a heuristic picture, which is meant to depict actually there's low energy excitations at the edge that we can see from putting the Landau level spectrum on a finite sample. And in addition, another way to see this is if we look at the band structure, in the bulk, there's an energy gap. But if we plot the band structure on a finite size slab, we'll see that this extra state comes up and connects the valence and conduction bands. And since that state wasn't there for the infinite system, we can deduce that that state must have weight only on the edges of the system. So these are kind of three different pictures to think about why we can see current in quantum Hall states, and also how can we understand what the edge states are. And the basic reason that we have this bulk edge correspondence is if you have these two different topological invariants which take on integer values, so say you have n equals 1 quantum Hall state next to a vacuum which is n equals 0, these things are both integers. And we already said that they can't change under smooth deformation. So then you might wonder, well, how can we get from n equals 1 to n equals 0? Well, the only way to get between them is to do an abrupt transformation, which is to have a low energy state sitting there. So you have two different insulators. Any smooth deformation will keep them insulating, but if you have a low energy state at their boundary, then that's no longer a continuous deformation. And that's the only way that we can resolve being able to change between these different integer topological invariants. But there's another picture, which is we don't need to actually look at surface states in order to understand the quantum Hall physics. We can actually get the Hall connectivity from the bulk. And so this is this expression was derived in a pretty famous paper, and this is called the TKNN invariant. And so another point of topological insulators is that although we kind of know them for their surface states, we can actually diagnose them from their bulk. And this is really useful because if you're doing numerics, maybe you don't want to have to consider a finite size sample. Then you lose translation invariance in one direction. So what I want to cover in this talk, or in this first lecture, is how can we understand the surface states of topological phases, and also how can we diagnose them from their bulk and thereby derive these sorts of topological invariants. And so you guys should feel free to ask questions at any time, as they were saying earlier, because this is great, lots of questions, yeah.
So what can you say about the fractional quantum Hall states?
Oh, that's a really good question, but kind of outside the scope of this. So the fractional quantum Hall states, so in order to get fractional excitations, we need to have interactions. Otherwise, we'll never escape this kind of single particle picture. And so in this talk, I'm only going to be focusing on non-interacting states. Right, but if we introduce interactions to this picture, then we can make a different story, which will give us fractional excitations.
Could you elaborate a little bit about the smooth deformation
Yeah.
or the adiabatic?
Yeah, so I'll say a little bit more about this maybe in a bit, but the point is, what do you consider a smooth deformation of something? It's actually basically saying, here's an energy gap. We're talking about insulators, so there's always an energy gap. And if you make changes to your system which are small relative to that gap, then you're not really going to change the physics. You have an insulator. And in particular, if you have an integer invariant, you can't change that integer. But what can change that integer is closing the gap, because once you close the gap, you have no meaning of small anymore, because small is always relative to the size of the gap. And so that's kind of the reason why we can have these, the gapless excitations that sit on the edge. It's actually saying in order to get from n equals 1 to n equals 0, we need to close the energy gap, because that's the only way to change the topological invariant.
So how do you count the number of nodes?
I can count it by measurement, which would be measuring the Hall conductance. And so the number that appears here is equal to the number of modes. And actually, in some experiments, they can spatially resolve. These modes actually sit in different places in space. So they've actually done some experiments where you can count them, literally count them in an experiment by kind of measuring one at a time, spatially resolved.
I understand the first diagram is a bit of a schematic.
Yeah.
How do you really, in your head, think about energy as a function of position? As in how do you force grain something? Or usually when we think of energy eigenstate of the entire system. So what does it mean to have an energy at a particular location in space?
Yeah. Well, if we have a finite size sample, then we lose the momentum as a quantum number anyway, so we can't talk about that. But what we can do is still look at, the system will still have eigenstates and they'll still have a spatial distribution. So we can think about, we can look at the center of these states, like the center of the cyclotron orbits, and then we can see, well, what are the energies of those, for a state that has a particular center located in space, what is the energy of that state? So that's one way that we can think of it. Another way to say that is, if you have certain energy states, then you put yourself in a box, you can ask, well, how do you see what happens to those energy states? And you could probably derive, like perturbatively, seeing that they need to start, the states which are nearest to the edge need to rise up in energy.
So this is only energies of states which are localized at a particular x. Does not include extended states?
So in quantum Hall, you can choose a gauge, which is, if we pick finite in one dimension and then infinite in the other dimension, we can choose a gauge where these orbits are infinite in one direction, but actually localized in space. And so that's where we can think of the centers of those. Yeah. Okay, good. So this is actually kind of meant to motivate the rest of the talk. So, so we want to be able to understand surface states and also how we can get a handle on these bulk topological invariants. And we're going to do this in crystalline systems, because there we have momentum that we can use as a good quantum number. And so the place to start is to say, what do we know about eigenstates in a crystalline system? Well, a crystal has translation symmetry. So if you have translation symmetry that commutes with the Hamiltonian, then every eigenstate that you have can also be an eigenstate of translation, and therefore has some translation eigenvalue. And then using Bloch's theorem, we can also say that each one of these eigenstates can be decomposed into two parts, a phase, and then also this other part, which is cell periodic. And so we always call these things U, and it turns out that these are kind of the relevant parts of the eigenstate that we want to use. And each one of these eigenstates is labeled by a K. We get the K from its eigenvalue under translation symmetry. So, and so these Ks, you can see that they are only defined up to reciprocal lattice vectors, because they only appear in a phase of the exponential. So that means that, that we only need to consider a finite number of K. And these finite Ks are what define the first Brillouin zone. So the first Brillouin zone is a set of all the Ks that we'll consider when we're looking at the eigenstates of the Hamiltonian of a crystal. And in one dimension, since the Brillouin zone is only going from minus pi to pi, we can think of this as a circle. But in two dimensions, since we have kx and ky, this shape, which is periodic, going from minus pi to pi in one direction in kx, and then also in ky, this forms a torus. And in three dimensions, it would be a three torus, harder to draw. So this is the picture that you can keep in mind when you're thinking of the Brillouin zone. In one dimension, it's a circle. In two dimensions, it's a torus. But the point is that now that we have these eigenstates of the Hamiltonian, and each one is labeled by a k, then we can plot the energy eigenvalues, and they'll also be labeled by a k. And so this is what we get as a band structure. We plot some k, and we see that we get some states here. And when we talk about different insulating states that are topologically the same as each other, what that means is that we pick some energy gap, and that energy gap can't close, and away from that gap, we can smoothly deform all the other states. And so we could flatten out these bands. It doesn't matter what we do as long as this energy gap remains open. So that's how we define topological equivalence of band structures. You pick one energy gap to keep open, all the other bands can be smoothly deformed into each other. Now, in order to get topological invariance, what we need is the Berry phase. So you've probably seen this sort of stuff before, but just to kind of get the notation all lined up. So the first object that we need is called the Berry connection. And we can think of this as capturing changes in the wave function. So these U's are the block wave functions. You can think of the derivative operator as kind of being a difference operator between U of k and U of k at a slightly different point. And so when we take the overlap of that with the original U of k, what you're really measuring is how much does the wave function change. And when we follow this around a closed path, so we go from our original state, do some path, and come back to the beginning, all we can do, since we're coming back to the same state, is acquire a phase. And so what the Berry phase is telling us is what's the phase that we get when we go through some closed path, which could be momentum space or tuning some other parameter. Now, why is the Berry phase only defined mod 2 pi? Well, wave functions, of course, have a phase ambiguity. And so you can ask, well, suppose I computed my Berry phase, but then I wanted to pick a different gauge. So instead of this state U of k, I have the same U of k, but with some phase in front. And this phase in front might have some k dependence to it. Then what do I get for my Berry phase? Well, we can plug into these formulas here, and we can see that the Berry connection will change by a derivative of this phase. And then if we plug into the Berry phase, we see that the Berry phase itself changes by an integral of a derivative. And so we know what an integral of a derivative is. It's actually telling us it'll give us phi at the end point and the beginning points of the loop. Now, since we're talking about a closed loop, the endpoints and the beginning point are the same point. And so the only thing that can happen to this phase, since it's defined in exponential, is that it can change by a multiple of 2 pi. And so the reason that the Berry phase is actually a phase and not a well-defined number itself is because of the phase ambiguity of wave functions means that it's only defined modulo 2 pi. The Berry connection is completely gauge dependent. There is no one defined Berry connection. But if we take the Berry curvature, which is the curl of the Berry connection, then this is a gauge invariant quantity because the curl of the gradient disappears. And so the gauge invariant quantities that we can always define for some block eigenstates are the Berry curvature and the Berry phase when we put it in the exponential, so these 2 pi, multiples of 2 pi cancel out. So this is kind of the fundamental tool that we're going to try to use to define topological invariance. So the first thing that we can do is look in one dimension. So I also want to say that when we take the Berry phasor on the Bruin zone, this is also called the Zach phase. These terms are used kind of interchangeably, but just to remind you of what the words are. So in one dimension, like I said, the Bruin zone is just a circle. And so the Berry phase is this Berry connection, UDU, integrated over this circle. And one of the interesting things is that there's actually a physical interpretation of the Berry phase is that it gives us the polarization. And so we can see this because there's a canonical substitution. Since x and p are canonically related variables, we can make a substitution where x goes to idk or k goes to idx. And so we can kind of heuristically understand this by, if we turn this partial k operator into an x, then we see that the Berry phase is actually kind of telling us the expectation value of x as we move around some closed path. And so that's heuristically how we can get polarization out of this, because polarization is basically the sum of charges over whatever path you define. So Berry phase in one direction in the Bruin zone is connected to polarization. Now you might wonder, well, the Berry phase is only defined mod 2 pi, but the polarization seems like it should be an absolute number. So what's the connection between these? Well, in an infinite crystal, the polarization is actually also only defined mod E. So we can see this if we consider some infinite, this is meant to be a 1D crystal of alternating plus and minus charges. We can ask, well, what's the polarization of this crystal? Well, if we choose the unit cell to include these two charges, then we get a polarization of E. But we could also choose a different unit cell which is centered on the electron charge, and here we'd get a polarization of 0. And so no matter which unit cell we choose, the polarization will always be an integer multiple of E, and so it's only really defined mod E in the same way that the Berry phase is only defined mod 2 pi. And so this is all consistent. The only thing that is actually a gauge invariant quantity, or it doesn't depend on our choice in unit cell, is differences in the polarization. Similarly to the Berry phase by itself is not a gauge invariant quantity unless we take it mod 2 pi, but we can compare two different Berry phases, and no matter what gauge choice we choose, the difference between them is something which is well defined. And the way that we can get this is just by acting with the time derivative on this formula for the polarization, and then we see that what happens is that you get out the curl of A, and we already saw that the curl of A is a gauge invariant quantity. So differences in polarization are well defined for infinite crystals, and this is how we're going to try to get to some topological invariance. And this whole idea is what's now referred to as the modern theory of polarization, and is summed up in these papers. So are there any questions about Berry phase at this point? Yeah, so the U of K is the block eigenstate. Mm-hmm. Yeah, this is a really good question. The Berry phase is always defined for a particular band or group of bands. So I've just been writing this U of K. If we have a bunch of separated energy bands, we can compute the Berry phase of each band. But you can also compute the Berry phase of any number of bands below the Fermi level or anywhere in the spectrum. Now, if you have multiple bands and none of them cross each other, the Berry phases will just add together. That's fine. If the bands cross each other, then what we need to do, this thing becomes matrix valued. Each of these states will have an index n. The Berry connection will then have indices on it, and then we take the trace of this thing to get one Berry phase. So if your bands cross, you can't talk about the Berry phase of each one separately, but there is still this kind of combined Berry phase of both of them. And you get that by defining a matrix valued Berry connection. And that's called the non-abelian Berry connection. Okay, good. So, okay, this is in 1D. And then the kind of classic model that illustrates this is called the SSH model, which is named after Sue Schrieffer and Heeger. And so what this model is, it was meant to model polyacetylene. So this is a chain of carbon atoms, and they have alternating single and double bonds. But we can see that there's two symmetry-related ways to draw this chain, which is, do the double-valued bonds fall between the same unit cell? So this index I is meant to be the unit cell, or do they fall within different unit cells? And we can make a simple model to illustrate this, which is just a tight binding model where we have this parameter delta, which is a dimerization parameter, and we can say, well, if we have a 1D chain of atoms, we have hopping between all the atoms, and then we can modulate, is the hopping alternating in strength between small, big, or is it big, small? That's what this Hamiltonian is capturing. And as long as delta and T are non-zero, then this energy spectrum has a gap. And we'll kind of always consider the limit where the dimerization is smaller than the actual hopping term. And so then the gap is given by, is proportional to the magnitude of delta. So how can we now get a topological invariant out of this thing? So the Hamiltonian here is I wrote it in this form. We can write it in a matrix form. It'll be a 2 by 2 matrix because there's two of these sites in the unit cell. And so 2 by 2 matrix for a Hermitian Hamiltonian means that we can write it as coefficients of sigma x, sigma y, sigma z, the Pauli matrices. And for this particular Hamiltonian, the Z Pauli matrix doesn't appear in it. And so we now have two parameters, which are the coefficient of sigma x and the coefficient of sigma y. And each of these parameters is a function of k. And so we can make a complex number, which is dx plus I dy, and we can ask, how does this complex number change as we move around the Brillouin zone, the one-dimensional Brillouin zone? And so it happens that in the case where this modulation parameter delta is less than 0, then this complex number dx plus I dy winds around the origin. So we say it has a winding number of 1. And this winding number turns out to be equivalent to the Berry phase. So it corresponds to a Berry phase of pi. But in the case where delta is greater than 0, then the winding number is 0. If we trace this complex number dx plus I dy, we never cross the origin. And so this winding number, which we can prove is actually equivalent to the Berry phase, gives us a topological invariant, which is, do we cross the origin or do we not enclose the origin? And that corresponds to a Berry phase of pi or a Berry phase of 0. And so this is kind of the one-dimensional example of how we can get topological invariance out of here. But the important thing is that this coefficient of sigma z is 0. Because if that coefficient is not 0, then what can happen is that without closing the bulk energy gap, we can change the winding number of this thing. We can change whether it encloses the origin or doesn't enclose the origin. And so then we destroy the fact that this is a topological invariant. So the important point is that we need to have some kind of symmetry, which in this case could be inversion symmetry or particle hole symmetry, that forces us to not have this term. Once we don't have that term, then we can make this complex number and we can ask how it winds around the origin. And it turns out, well, as we said, this Berry phase corresponds to polarization. So this, we can see that these two different phases, delta less than 0 and delta greater than 0, they differ by a Berry phase of pi. And if we look back at our polarization formula, that would be a polarization of E over 2. And so we can think of this as, well, if we take this model, however the eigenstates look, and we compute the polarization wherever it is, as we change from this model to this model, so kind of modulate delta, we can see that what we've done is shifted by half a unit cell. And so it makes sense that the polarization has changed by E over 2. And so we can interpret this difference in Berry phase as a difference in polarization. And one of the physical consequences of this is we can then ask, well, what if we put these two states next to each other? So if we consider delta greater than 0 and delta less than 0, where they hit, there'll be this defect state, which is where there's two double bonds instead of alternating. And so at this defect state, or at this defect position, we can ask, well, what happens to the spectrum there? And it turns out that there's always a domain wall state which is sitting there. So there's some low energy state which is sitting right at this interface. And we can think of this because there's a change in polarization, and so there's kind of a conflict of where the extra charge should be. But we can also derive this. And so the way to derive it is to say, we have the Hamiltonian from the previous slide. We can write a low energy theory. So we saw here that the low energy physics is all happening near k equals pi. So we can take this Hamiltonian, expand around k equals pi, and expand for small delta, and then we'll get this low energy continuum theory. And to make the domain wall, what we do is we want to change delta from greater than 0 to less than 0. So we give delta this kind of space dependence. And once we make this low energy theory and make delta have the spatial dependence of a domain wall, then this maps to what's called the Jackie-Rebbe model. So this is another kind of famous paper which is showing us how to get these edge states. But what this paper shows is that this eigenstate that I've written here is actually an exact eigenstate of this continuum theory when I have this spatial dependence on delta. And furthermore, this eigenstate is exponentially localized right at the domain wall. So this is a general feature where if you have a mass term like this, which is our delta term, and it changes sign, sitting right at the sign change is going to be some state. And the quicker it changes sign, the more localized that state is. So this is another example of the bulk edge correspondence where we have these two different states that have this different Berry phase in the bulk. The Berry phase is quantized by symmetry, which is what gives it the winding number. And when we put these two states next to each other, there's a localized state which is sitting at their interface. So, yeah?
Can you elaborate on how the winding number is related to the Berry phase?
Yeah, so I think it's something that maybe we need to compute it to see. Let's see. The Berry phase is capturing how the states change, how the eigenstates change as we move k in a closed loop. The winding number is also doing that same thing. You're tracing out some path of dx. So you can think of it as, do you want to trace out a path of the Hamiltonian, or do you want to trace out a path of eigenstates? This dx plus idy is actually tracing the Hamiltonian, but the eigenstates will move along with that. And so you could if you followed the steps, you could prove that these are actually the same phase. But I don't know if it's more intuitive than that. Mm-hmm.
So in this case, it was important that the Hamiltonian didn't have a sigma z.
Yeah.
So I think that so we can say
Yes, we can do exactly something like that. So what happens is kind of at the end of this, I'll show a table which is capturing this exact question, which is if you have symmetry in a certain dimension, what's the topological invariance that you get out? So this is a very simple example because it only has 2 by 2 matrices, and so we can actually do this winding number. If we had 4 by 4 matrices, the picture wouldn't be so simple, but you can get the same result out. And one way to think about this is you have a particle hole symmetric system. Do you have an eigenstate at 0 energy or do you not? And you can see that you can never change that by smoothly deforming the Hamiltonian because states always need to be added in pairs. So that's the kind of more general way to think about it. Okay, good. So the main takeaway of this is that we have the SSH model in 1D. Berry phase turns out to be a good topological invariant as long as we have the symmetry constraint. Sitting between these two states, we see this bulk edge correspondence. There's a state at the interface. And so the next thing that we can consider is what can we do if we smoothly interpolate between these two states? So in order to smoothly interpolate and to leave our gap open, then we need to add in this sigma z term. Otherwise we're necessarily fixed. We can only have delta greater than 0 and delta less than 0, and the gap has to close in between. But if we do this, and if we can make some way to move between these two states, then what we'll do is slowly end up moving charge across our system. So we can consider doing this as a function of time. So suppose we have our Hamiltonian at t equals 0, and so I'm now using this picture. It's a slightly different picture. It's basically just meant to say, if we have a polarization of 0, we can think of these electron charges as sitting on top of the nuclei. Now, as we just said, the polarization is only defined modulo E, so there's some ambiguity here. But if we pick this as our starting point, what we can see is that suppose we now tune into the other phase where the polarization is E over 2. Then no matter how we did this, we necessarily had to move all the electron charges over by a half. Even if there was some ambiguity in our starting point, we can compare these two states and see that that's the thing we need to do. And if we kept doing this, then we would move the charges over by another half. And then we get back where we started. So we can imagine some complete loop where we started out in some configuration at 0 time. We slowly slide our negative charges until they've shifted by exactly 1. And now the beginning and the end configurations are exactly the same as each other in that we have a polarization of 0 for the unit cell that we chose. But throughout this process, we can see that we've shifted. The change in polarization is actually a whole electron because we've moved everything over by 1 unit cell. And so we can ask, when we make a cycle like this in time, how much charge have we moved? And it always needs to be an integer number because if you're starting and ending at the same point, the only thing that you can do is change integer numbers of charge. Because we need to get back to the same picture where the plus and the minuses are sitting on top of each other. And so then we can ask, well, if we have a charge pumping cycle like this, what's the change in polarization? Well, we just argued since the beginning and the end states are the same that change in polarization needs to be an integer number of electrons. But we can also apply this formula that I wrote earlier, which is the derivative of the polarization will end up giving us this curl of the Berry connection. And so we can see that by relating this expression and the fact that after 1 full cycle we can only pump integer numbers of electrons, that this expression here must give us an integer number. It's not obvious from looking at it, but we know that this has to be true. And this integer number is what's called the Chern number. And so the Chern number is what characterizes whenever you have block wave functions of 2 different variables. So in this case, we're tuning something as a function of time and also as a function of momentum, then we can always define a Chern number of it. And so in this example, the Chern number would be 1 because as we've moved through this cycle in time, then we've pumped 1 electron from the left to the right. And the other way, so again, going back and forth between this Berry phase and polarization, we can also think of this Chern number as the Berry phase winding from 0 to 2 pi. So if in our initial state we had a Berry phase of 0, and at halfway through we reached the other state where we had a Berry phase of pi, and then we kept going in that direction, then we can see that at the beginning and the end, We have a Berry phase of 0 and a Berry phase of 2 pi. So these are the exact same state. But actually, we've done something non-trivial in between, which is we've moved across and we've completed like one full winding cycle of the Berry phase. And so it turns out that this is actually a practical way to compute the Chern number. You can compute how the Berry phase changes, take the Berry phase in one direction, which for us is k, compute how it changes in the other direction, which is time. And if it does this complete winding from 0 to 2 pi, then that means we have a Chern number of 1. If it winds around twice, then we have a Chern number of 2. And the way to see that this Chern number always has to be quantized is we know that from the beginning and the end, we need to reach the same point. So there is no way, once we've gone from 0 to 2 pi, there's no way to break this. There's no way to say, well, what if we didn't get to 2 pi, we just made it to 2 pi minus epsilon? Well, that's not possible, then we wouldn't be at the same state. And so the Berry phase can only wind in a complete cycle by a multiple of 2 pi, and how many times it winds is exactly the integer invariant, which is called the Chern number. Mm-hmm.
Yeah, so if I look at this picture, I see that it does not depend on how quickly I do it.
Yeah.
So if I make the Hamiltonian time dependent and I do it very quickly, this picture will still hold.
Okay. What can happen? Yeah, what can happen? We always have this energy gap, and so for our system, say we have valence bands and conduction bands, and there's some energy gap in between them. We want to capture the Berry phase of one particular band. If we move too quickly, we'll jump across the gap, and then we won't be targeting this band. So Hedman et al. Said something about this transformation being adiabatic, but there is the energy gap which is sitting there, and yeah, so that's how that enters. Mm-hmm. Right, there should not be any path dependence of this, except as you change which way you move around the torus. So in our case, we have a Berry phase in one direction, and we're plotting it as a function of time. Now, we could have maybe taken the Berry phase in the other direction and plotted it as a function of k. So there could be path dependence for different loops. Since the Chern number is a good topological invariant, it wouldn't matter for us. But as long as you take the same loop around the torus, then there's no path dependence. Are there any other questions? Okay, good. So, so now we have two invariants. The Berry phase, which is not always quantized, but with symmetry it can be quantized. That goes in one direction. And the Chern number, which is a topological invariant in 2 dimensions, and we can think of it as how does the Berry phase in one direction wind as we plot it as a function of the other parameter. So we can apply this, so now going back to the quantum Hall state, we can apply this kind of similar logic. And so the steps for thinking about this are we can follow the same charge pumping argument in one higher dimension. So the way that we do this for a quantum Hall state is we take our 2-dimensional quantum Hall state and put it on a cylinder. And then through the middle of that cylinder, we can thread one flux quantum. And so we can follow this, to follow the steps, what we need to do is say, okay, we thread one flux quantum. According to Faraday's law, this generates an electric field. The electric field will be winding around where the magnetic flux is. Then since we have a Hall conductance, or if we have a Hall conductance, that electric field will, of course, give us a current. And so then we can ask, well, if we have a current which is moving along our cylinder, how much charge is pumped from one edge of the cylinder to the other edge of the cylinder? And just by plugging in these equations, so if we say the change in charge is equal to integrating the current over one full cycle, then we see that we get out the Hall conductance. But the question is, well, how do we then prove that the Hall conductance is a quantized number? Well, if this insulating system has an energy gap, then threading one flux quantum, this is actually from step 0, and if we compare time 0 and time t, this is a transformation which can be gauged away. So the Hamiltonian is exactly the same at the beginning and the end. So all the eigenstates are exactly the same. The only thing that we can change is the occupation number of these eigenstates, which is exactly how much charge we've pumped. And so And so if we want to compare the state at the beginning of the cycle and at the end of the cycle, the only thing we can do is change the occupation number, which is changing an integer number of charge. And so this is the same argument we made in the 1D Thales pump, which was if you start with your polarization at some value and you make some complete cycle, you might be moving charge, but all that you can do is change it by an integer amount over the full cycle. Otherwise, you wouldn't have returned to your beginning point. And so it's the same argument here. If you want to return to your beginning point, what you have to, since having exactly an integer number of flux quanta will leave the Hamiltonian invariant, then all you can do is change integer numbers of charge. This is another reason why we can't get the fractional quantum Hall effect out of this sort of logic. So by comparing this expression for the change in charge and this expression for the change in charge, we can see that the Hall conductance has to be this multiple of E squared over H. And so this is kind of the steps that we should get to compute the Hall conductance, which would lead to the TK&N formula that I showed earlier. And so if we compare these things, this is their formula written in terms of the Berry connection. We can see that this N that appears here, it's exactly this N, and this is exactly the formula for our Chern number. But now, instead of previously we talked about the Chern number on a torus where one direction was k and the other was time. Now we're talking about a Chern number of a two-dimensional system where both of the directions are k's. They're just two different k's, and this is the exact same Chern number. So we can compare this 1D Thales pump and this 2D Laughlin argument for explaining quantum Hall with basically the same plot, which is they're both described by a Chern number, but the axes or the parameters in our Hamiltonian might be T or might be K. And if we look at the energy spectrum, we can see for our quantum Hall state, I already showed this plot. If we look at the energy spectrum for a finite size sample, which has only translation invariance in one direction, then we see that there's this extra edge state that appears as a function of K. But in the Thales pump one-dimensional system, we can plot as a function of time, and we'll actually see the same thing. But now it means something different. It means that we have a one-dimensional gap state, and there's each one of these lines is a different one-dimensional state as a function of time. And there'll be slowly one charge that's pumped from the valence band to the conduction band as we chart this thing as a function of time. So the 1D Thales pump and the 2D Laughlin description of quantum Hall are actually kind of capturing the same thing. We're just trading time as a parameter or momentum as a parameter. And this is another way to see this bulk edge correspondence. The Chern number is exactly what gives us the topological state in the bulk. But if we follow the polarization or the Berry phase or the edge states, then that's what describes the physics going on at the surface. So, and then there's one other point about the bulk edge correspondence. I've been drawing these very simplified pictures which have kind of a straight band here, but this doesn't have to be the case. So what the topological invariant tells us is that there has to be one surface state, and it has to connect the valence and the conduction band. But it can have any dispersion, and in particular, it can also go up and come down. And so this surface state diagnosis of a quantum Hall state or any state with a Chern number, the way to do it is if you draw your Fermi level as a straight line, you have to count the number of bands that cross it, and you count them with their slope. So bands that cross with positive slope count as a +1. Bands that cross with negative slope, like this one, count as a -1. And then so subtracting the minuses from the pluses gives us a practical way to get the Chern number. And this also gives you a hint at why this is actually a topological invariant, because you can see that we know that a topological invariant should be unchanged under smooth deformations. And so if we take this band, a smooth deformation would surely be pulling that band around. But once we kind of pull it below the Fermi level, we always introduce pluses and minuses in pairs. And so they'll always cancel in this formulation. And so it makes sense that the topological invariant would be taking the differences between the plus states and the minus states. And so the point is that the bulk edge correspondence kind of tells us the net value of states that are crossing the Fermi level, but doesn't actually have to be one. It could be more than one, and there could be some funny dispersion. And if we had a Chern number of 2, there would be 2 such states, et cetera. Is what part proven? I think it is, yes, I think it is proven. It's basically just relying on the fact that you could always make a model which had this straight line state, and then as you smoothly deform I think that basically is the proof. As you smoothly deform this line, you'll always introduce pluses and minuses in pairs. And so you could always undeform it to make it straight, and that gives you kind of the usual thing.
I guess I was thinking more in terms of where you define Chern number in terms of the
Mm-hmm.
from there.
Yeah. So I have a reference later, but yeah, there's actually at least one paper which is explicitly showing. So there is something else interesting here, which is that this surface state kind of follows the Berry phase. So the Berry phase wound one time. The surface state there's one surface state of positive slope. You can actually make concrete provable statements about this by saying, how about we look at our Hamiltonian, flatten out the conduction and valence bands, so that would be a smooth deformation, putting them at, say, +1 and -1, and then looking at the states that need to connect them. And in doing this, you can kind of map your Hamiltonian to a unitary matrix, and then you can classify things about that unitary matrix. And so this correspondence between winding Berry phase and number of surface states is provable. And once you have a winding number, it doesn't matter about the path that you take. And so these kind of loops, which would contribute to writing it in this form instead of just counting the number of bands that cross, they don't contribute to any changes. So does that answer your question? Not quite.
Well, what you just said is basically topological insulator classification.
Mm-hmm.
But that still is in the realm of doing stuff in bulk.
Mm-hmm.
Basically, you treat, like as you said, you flatten all the bands, right? And then you can basically interpret your, let's say, your Chern number as a map from your bronze.
Yeah.
Like
Yeah.
and there's some topologically not trivial stuff going on, but that still also relates to the edge. I think
Right.
that you need the idea of singular convex theorem, right?
Yeah. So I guess what you can do to think about the edge is you have this bulk classification. If you put it on a manifold with an edge, if you treat it as a field theory and put it on a manifold with an edge, then you'll see that there's an anomalous term that appears on the edge, which will exactly kind of compensate for the anomalous term in the bulk, which gave you your bulk topological invariant. And these things have to map into each other. So for quantum Hall states, this has been done explicitly, where you take your bulk field theory, get the anomalous term on the edge, that gives you an edge field theory, and that tells you exactly what's going on the edge. So that's, I think in that language, that's a way that you can go between the bulk and the edge. Heuristically, there's also an argument, which is the thing I was saying, if you have integer invariants, the only way to have them change is to have the gap close, and therefore you need to have a state there. And that sounds very heuristic, although it does sound logical, but you can make it more concrete by using this Jackie-Rebbe way of computing edge states. So it's not, it sounds a little bit hand-waving, but actually if you looked at your for any particular model, you can look at the Jackie-Rebbe formulation at the edge, and then you could actually derive this line of edge states. But what you can see is that the surface potential that you have would allow you to have these sorts of kinks in the band structure. So, yeah. Mm-hmm.
What happens if it kind of becomes like an inflection point where the slope will basically go to 0?
Right, so this is ignoring kind of pathological points like that. So then you could reach some, like this is actually almost like that point, and you might say, well, what's n plus and what's n minus? You can always compute your Chern number in the bulk, and then you will never have that problem. And you could always probably add a small perturbation to your surface to get rid of the inflection point, since it will be a fine-tuned point. So a person shouldn't worry too much about that, although that's a good question. Okay, good. So in the last few minutes or 15 minutes of this, I want to say we can add symmetry to this, and that will enhance our classification. And so the most straightforward symmetry to consider is time reversal symmetry. So for fermionic systems, what does time reversal symmetry do? It takes k to minus k, and it's also anti-unitary, and it squares to -1. That last bit is particular for fermions. And so if you have an anti-unitary symmetry that squares to -1, you get Kramer's pairs. The Kramer's pairs will always be between k and -k. Those ones aren't so relevant to us. What's interesting is that at k equals 0 and k equals pi, so those are the momenta which are invariant undertaking k to -k, then the Kramer's pairs are sitting at the same k point. And so you can see that the existence of these Kramer's pairs, first of all, it forbids having a Chern number, because if you have a Chern number, you will only have one state here. You won't be able to have pairs. And if you had a symmetry, so you could say, well, maybe I have a Chern number of 2, then I'd have a Kramer's pair, but then you won't have the symmetry of going from k to -k. So the Chern number is always 0, but what we can have is surface states that cross like this. And so if we were only looking at Chern number, we would say, well, this is trivial. But the fact that these two states are pinned to each other because they're Kramer's pairs, and that pinning happens because of time reversal symmetry, this surface configuration, these states can't be broken. And so we can definitively say having one crossing point here is a different sort of insulator than having no crossing points. And that's kind of the surface diagnosis of a topological insulator with time reversal symmetry. And so we can think of these two bands that cross as giving us two different surface states, one of positive slope and one of negative slope, which translates to having positive and negative momentum. And so again, if you didn't have any symmetry, these forwards and backwards moving states can gap each other out because they could scatter off of each other, but it's the time reversal symmetry that prevents that from happening. And so this defines a Z2 topological invariant. So the Chern number is a Z invariant, which means it takes integer values. Z2 invariant can only take two different values, which is 0 or 1. And we can think of this 0 or 1 being, if I look at half of the Briand zone, so now starting at k equals 0 and going to k equals pi, how many bands are crossing? Is it an even number or an odd number? And so you can see in this picture, if I say take my Fermi level to be here, I only have one band crossing it. And so that diagnosis of having an odd number tells me that I have a non-trivial Z2 invariant. And similarly as before, I could make this band dip down or have some type of dispersion that wouldn't change the odd or the evenness. So that's kind of the practical way to compute the Z2 invariant. You look at the surface states and you look from k equals 0 to k equals pi, and you count the number of bands that are crossing. If it's an even number, you have a trivial state. If it's an odd number, then you have a non-trivial Z2 invariant. So there's a complicated formula for computing this in the bulk. So this would be the generalization of the Chern number. There's some other bulk invariant, and it takes this form, and it works, but in practice, it's very difficult to compute. So what are some practical ways that we could compute this? One practical way is to, again, go back to our Berry phase. So now, if we have an insulator, if we looked at the occupied bands, there always has to be an even number of them because of the Kramer's partners. And so now we can look at our Berry phase, and it's always going to consist of at least two bands. And what happens for a topological insulator is that the Berry phase will have this feature of crossing at 0 at one of the trim points. So this is at k equals pi, and then crossing at pi at the other point. So this is like a double winding. For the Chern number, we saw that the Berry phase went from -pi to +pi. For a topological insulator, there's two bands, and what they do is they cross at one point, and then at the other k point, they cross at pi. So this picture on the right would be a trivial insulator. You can see that at k equals pi, the Berry phase of both bands is 0. And at k equals 0, Berry phase of both bands is 0. But for the topological insulator, at k equals pi, the combined Berry phase is 0, but at k equals 0, it's up at pi. And the reason these Berry phases are subject to the same Kramer's pair constraint, so they always have to be partnered in this way. So a practical way of computing the Z2 invariant is to compute the Berry phase of your multiple bands and see if they make this winding picture, and then counting the number of crossings that you have. If you have an odd number of crossings, then you have a non-trivial Z2 invariant, and if you have an even number of crossings, which in this picture is 0, then you have a trivial Z2 invariant. And you can see, like, even if you moved your Fermi level up, then we have two crossings. So you can kind of see by moving around where your Fermi level is, it'll always be an even number on the right-hand picture and an odd number on the left-hand picture. And this is kind of going back to what we were talking about before. the Berry phase imitates the surface spectrum, and this is one paper where this is made rigorous, doing this flattening procedure that I was mentioning. And on another practical level, I just wanted to say there are some software packages, this is just one example, which will compute the Z2 invariant for you. So if you have some tight binding model or some output of a DFT calculation, you can put that into this sort of Z2 pack, and it'll spit out the Z2 invariant for you. But if we don't want to compute the Berry phase, then then we can also, if we have extra symmetry, find some other routes to computing the Z2 invariant. So one route is if we have spin conservation, then the up and the down spins separately we can diagonalize the Hamiltonian separately in terms of up spins and down spins. And the Z2 invariant there just corresponds to having a Chern number separately of 1 for the up spins and of -1 for the down spins. Then we can use our previous work on the winding Berry phase for each spin separately to get at this Z2 invariant. And then the other thing we can do is if we have inversion symmetry, then at each of these trim points, we can get an inversion eigenvalue. And if we multiply the product of these inversion eigenvalues, that's another way to getting the Z2 invariant. So the Z2 invariant takes a complicated form, but in the presence of symmetry, we can calculate it more easily. And if we compute the Berry phase, we also have kind of a direct route to calculating, a direct and practical route to calculating it. Mm-hmm.
So in the practical scheme that you highlighted in the earlier previous slide, so here you have the Berry phase calculated at each ky.
Mm-hmm.
And so if you're doing that numerically, you have some prescription that makes the phase continuous as you're changing y, as you're changing ky.
Yes. So the Berry phase, well, it's always only defined mod 2 pi. So the only fear would be that, say, these bands would end up shifted by 2 pi. So you'd need to enforce a continuity constraint, which would be, say, restrict your Berry phase between -pi and pi, and that would automatically make it continuous. It will only be continuous, of course, up to the discretization of your K-grid. So, and I also actually wanted to say there is, why is this not the exact same thing as computing a bulk topological invariant? Well, you do have a finite mesh of your K-grid. And so you could always be worried about some pathological winding that you're not going to pick up on. And so this method is only as good as your K-grid. And that's kind of why if you compute the bulk invariant of your model analytically, you will always get the right answer. If you do this numerical method, you're making an approximation. On a practical level, if you have a normal model, why would you expect a pathological wind? You know, you make your K-grid small enough, you see that nothing is changing, you can trust your results. But as you get closer and closer to the phase transition, this winding will happen in a smaller and smaller range, and then you can't, then the numerics are harder to trust. But this is always the case when you're close to a phase transition, you know, then you need to do kind of tighter and tighter numerics to compensate for that. Mm-hmm.
So one of the ways in which we think of Chern numbers is an obstruction to defining a continuous phase
Mm-hmm.
over the entire ring also. And I'm wondering how one would reconcile that way of thinking of a Z2 invariant or a Chern number with like curves like this in which you are able to define a continuous gauge over the entire ring.
It's not really a continuous gauge because the gauge is hopping from 0 to 2 pi. So this is the problem. You have this whole gauge, but when you went back to your beginning point, you shifted from 0 to 2 pi, and that's what the obstruction is. Okay, good. So this is kind of practical calculation of the Z2 invariant. And probably the last thing to point out is that, okay, we've made this pretty abstract. How can we realize this? The original idea by Cano and Melee was to realize this in graphene with spin orbit coupling. So graphene has these Dirac cones which are linearly dispersing, so they're gapless. But we can ask, how do we open an energy gap in here? And it turns out that there's kind of three different ways to do this. One way is to add a sublattice potential. So you have these two different sites in the unit cell of graphene. We can add an energy to the red sites and not to the blue sites. This will break the symmetry of the lattice, and it will give us a trivial insulator. The other thing we might think to do is to add flux through these different unit cells. And this actually gives us what's known as the Haldane model. We can add opposite fluxes depending on if we traverse, kind of make a loop around the blue sites or around the red sites. So on the whole, time reversal is preserved, but locally it's broken. And this broken time reversal means that when we introduce a gap in this form, that we get the quantum Hall effect. So the way that we're interested to get a TI is to introduce spin-orbit coupling. And so that's the result of this Cano paper. We introduce spin-orbit coupling, we preserve all the symmetries of the lattice, but we can still open a gap, and this is how we get the Z2 invariant, or the quantum spin Hall effect. However, in graphene, spin-orbit coupling is going to be a small quantity, and so physically, this isn't really relevant. It's a toy model result. And so the actual case, which is considered to be the physical realization of the quantum Hall effect, of the quantum spin Hall effect, is in these mercury telluride, cadmium telluride quantum wells. And so in these situations, spin-orbit coupling is sizable, and what happens is that in cadmium telluride and in mercury telluride, the difference between these two things is that the gap closes and opens. So one of them is a conventional insulator, the gap closes and opens, and the other one becomes a non-trivial topological insulator. And so the genius was to kind of put mercury telluride in between cadmium telluride, make this distance small, so this is effectively a two-dimensional system. And when the mercury telluride layer is large enough, then you get a two-dimensional system which has this topological band structure of mercury telluride instead of the trivial one of cadmium telluride. And this is what was actually carried out in experiments. And so they look at these two different regimes. One regime is when the width of this quantum well is too small, and so you don't actually get the physics of the mercury telluride coming in. And here you see that the conductance is perfectly zero. It's a bulk insulator, and there's no surface states. Now, when we move to the topological regime, which is where this width of the mercury telluride quantum well is large enough to capture the physics of it, then you see that you get this conductance of 2e squared over h. And then 2 is coming from, you have actually two modes moving in each direction, one from the top edge and one from the bottom edge. And they measured that this quantized conductance was independent of the sample width, which is showing us that it's coming from the edge physics. So, right, so this is actually pretty cool because we've spent a lot of time talking about these abstract Berry phases and abstract topological invariants, and so I want to point out that these are actually realizable in a handful of physical systems. And then just to flash through what would we do in 3 dimensions. In 3 dimensions, what we can do is consider the two-dimensional index of different planes, k equals 0 plane and k equals pi plane. And we can do this in all different directions, and that gives us 6 different invariants. But they're not all independent of each other. And so what happens is that there's 1 strong index and 3 which are called weak indices. And what these strong and weak indices correspond to is, instead of Kramer's pairs, we get whole Dirac cones. So in a 3-dimensional system, the surface is 2D, and so a band crossing in one direction has to actually be rotated around both 2 directions, and that gives us a Dirac cone. And so for a topological insulator in 3D, on the 2-dimensional surface, you'll see 1 of these Dirac cones. And for these weak indices, what happens is you see 2 of these cones. And the reason that this is called weak is because if we broke translation symmetry, these 2 cones could map on top of each other. So if we enlarge the unit cell, we'd fold the Brillouin zone, and thereby you could open a gap. If you have 1 of these cones, you can't do that. And so, so this is what's called a strong Z2 topological insulator. And there's some constructions for this, and we can talk about this later in the tutorial. This is also realized in some materials. So the final thing that I wanted to show was now we showed, so I said quantum Hall doesn't require any symmetry. The Z2 topological invariant requires time reversal symmetry. What are the other symmetries that we can have? And it turns out that there's 10 different ways that we can classify matrices. And so this is called the 10-fold way, which is saying, do you have time reversal or do you have charge conjugation symmetry? What combination of these things do you have? And do you have fermions and do you have bosons? That comprises these 10 rows in the table. And so we can see if we look in the class A, which has no symmetry, in 2 dimensions we have a Z classification. That corresponds to the Chern number or the quantum Hall invariant. But if we go to this class A2, which describes fermions with time reversal, we have Z2 classifications in 2D and 3D. These are the Z2 invariants that I was describing. So, the final message is that you can look at all the different possible symmetries that you can have, This is the table that captures them all in different dimensions. And so this is the place where we can kind of definitively look for topological invariants. So I think this is time to stop. Are there any kind of quick last questions? And we can chat over the coffee break if there's more.